Yeah.
Yeah, so thanks for coming. So it's supposed to be a slightly different kind of talk series. Hopefully, you have 1 or 2 talks per semester. And the idea is to have people who are using ideas in systems and computer science to solve hard, challenging problems, and have them talk about what those problems are, what are the parameters, what they need to solve them, what is considered hard, what is considered doable, etc. So our first speaker is Ankit Saxena from Marvell. Ankit has been working on design and verification of semiconductor circuits for about a decade. Before that, I think he also had experience in working in nuclear energy. So, yeah, so it's completely real work. And I really go back a so I can talk like this. Go back a long way. Like, you shared a wing that was still very much in project. So with that.
Thanks. Yeah, thanks, Piyush. So yeah, I've been part of the semiconductor industry for like 12 years now, and almost 12 years I've been a user of Affiliation. So yeah, in today's talk we are going to talk a little bit more about that. And right now I am working as a principal engineer in Marvell Technology. Marvell with a double L, not that straight one. Okay, so what I'm going to talk about is a little bit of the basics, so that we can make sense of the things that we are going to talk about later, and then I will talk about the little bit about why formal verification is required in today's world, and then the challenges, a little bit of limitations if we have time. And what I am not going to talk about is this, because I've always been a user. So frankly speaking, I don't know much about this part. Right? So let's start with that. So starting with the basics, like anything else, things get started with the requirements. And after the requirements, we come up with a specification and architecture for the end product that we want as a chip, semiconductor. Right? From the specification and architecture comes the next step, the design. And design happens in hardware description language. Mostly people use Verilog, system Verilog these days. In the past, VHDL was also used as a hardware description language. There are more, but not that commonly used, mostly Verilog system. And then comes this step of verification, which is basically our focus here in today's step. This step is basically just to ensure that this design matches the specification. And then of course, after this design, that this model, which is still a part of, it's still in a form of STL, gets converted to the netlist, which is gates flip-flops. Okay. And then after that, since there is a conversion happening, we again need to verify this against this, because we need to ensure that nothing changes during the conversion, right? Nothing changes logically or functionally, and then goes to the fabrication units. And then there are some other steps as well, but this is the basic design flow. And in that design flow, these two gray boxes where the verification comes in the picture. The first one is functional verification, the other one is equivalence. In the first one, what we do is we verify the design against the specification. Right? If it matches, if it good to go, doesn't match, we need to change the design. The common methodologies that are used at this step are formal simulation and simulation. I'll touch base on formal and simulation. Simulation, you can think of running this design on an FPGA board, okay? And then observe that is it working okay or not. But this is something it is used for very limited, or I would say specific use cases. I'm not going to touch this one, but yeah, I will talk about these two. This one, then equivalence needs to be established between this and this. Their formal is mostly formalization. And I'm going to touch a little bit on this one.
So they said after you convert the from hardware description language to net list, you still do a verification.
Yes.
So the conversion process itself doesn't come with a guarantee that it maintains the same.
Yes, I mean, they try to maintain, but I mean, of course, it's not guaranteed. So it needs to be verified that this conversion doesn't introduce anything, you know. That something that we do not know. Okay. Now, another basic thing about, since we are going to talk about the verification, a couple of terminologies. So design under test meaning the design that we are verifying. For verification purpose, what we need is, if we go pretty low level in the design, we have some inputs and we have some outputs, right? That's how it is. To verify that, what we need to do is that we need to have some generator that generates the stimuli for us, and then of course we need to have some checkers that checks the output behavior, right? So this is I mean, as simple as that, nothing fancy. Okay. Now, so after that, now I'm going to move why formal is essential, but before that, just one statement that simulation is the mostly adopted methodology. Formal usage is pretty low compared to simulation, but it's increasing day by day. Why is that? We'll come to that in the coming session. Okay. Now, why formal is essential? Okay.
So the simulation is more like testing, or is it?
Both are testing. I will in the coming slides I will just go through some differences. But you can think of simulation as that like we saw in the previous diagram, we have this generator. Simulation is that we generate we using some tools and some you can say some programming languages plus tools, we generate those inputs and then we check those outputs, right? Again, using those tools and programming languages. We do similar thing with the formal also, but with some differences. That yeah. Now, yeah. So in today's world, designs are getting complex and complex each and every day. And why? Because of the increasing performance requirements, right? And it's just not very easy to handle those requirements. I mean, of course, we cannot get right away increase the clock frequency. I mean, there are challenges that, of course, we are all aware of. I'm not going to touch that. This problem is solved at the architecture level itself. So how do people solve it? One example is parallelism. People, the architectures, they introduce parallelism in the hardware design. One example could be multi-cores, right? We have always seen those processors having multiple cores, right? One example. Other example could be hardware accelerators, right? Hardware accelerators means some part of the hardware that is doing, for example, encryption for us. Otherwise, to do the encryption, we'll have to go through the software layer of the design, right? Software will control the hardware to do the complete encryption for us. Instead, if we use just a piece of hardware that can, do the encryption for us using a single command, right? Using a single, let's say, single output, a single instruction that speeds up the process, right? That makes sense, right? Yeah. So this increasing performance requirements, this problem, to tackle this, people have been solving using architecture innovations, but it comes with own prices, right? As soon as the architecture becomes complex and complex, the verification of it becomes harder and harder. Yeah. There's a
in hardware earlier you have to check that it's adding correctly, but now it's implementing AES correctly.
And of course, with the parallelism, with parallelism comes concurrency, right? Now there are multiple, if we look at, if you take a very simple example, right, of a scheduler, right? take a very simple example of a scheduler. As the parallelism increases, it needs to take care of multiple requests, right? Let's say scheduling for some memory, right? Memory. There are multiple CPUs, right? Which are trying to access. Now it needs to take care of that, right? Then if the memory is shared, then the problem becomes more complex. Because of coherency, it needs to ensure coherency, right?
There are more situations.
More situations. I mean, by coherency, I mean it needs to ensure that each CPU sees the same value of the memory content at any address. Right? This becomes more. I mean, this makes the whole system more complex. So yeah, so this Wilson research group it did a study in 2020, and they come up with the following data that in the year 2020, 68% ASICs were behind schedule.
So what is ASIC?
What is the ASIC? ASIC stands for application specific integrated circuits. Check.
But not like some general purpose.
Yeah. 60% of the ASIC needed reskin. Reskin means once you send them to fabrication, it comes back and they got to know it had some bug. They need to send it back. It's very costly thing to do. Millions of dollars are involved in sending ones. 50% of the time, the issue was functional, logical or functional, and about 70% of times
So what's the remaining? It's like in the manufacturing process.
yeah, sometimes manufacturing, sometimes there are other concerns.
So is there any difference between logic or functional? Like logic or functional, they're the same thing.
Yeah, for our discussion, I think. So now two things. One thing that I earlier mentioned, that simulation is still mostly used, right? Plus this study results. If we look at these two things together, this basically tells us that the traditional simulation based approach that industry is using up to now is that approach alone is not sufficient. We need to have something, and that something is formal verification. Using that, we can catch these corner cases bugs easily, and then of course we can. And formal actually also helps catching them early in the life cycle, which can reduce the time to market and help the companies in saving some dollars. How does that happen? So now we are going to see those differences in the format. So we saw this diagram earlier in one of this, right? We have this generator, designer, this, and the checkers. What happens in simulation that some team or some verification engineer needs to write the code for this, provide it to a simulation tool which can execute that code to generate these inputs, and then of course write these have these checkers and then do the verification.
And this will not be exhaustive, right? So it will only generate some of the process.
Yes. I mean, because it involves manual intervention. With formal, what happens is that the formal tools, they generate every possible scenarios for us. So we don't need to worry about generator. The tool does it for us. And the way it does, I mean, maybe we will have one more slide for that. And the way it does is that on each clock cycle, it basically drives all the possible values of each input at each clock cycle. So let's say if an input is 3-bit byte, meaning it can have value 0 to 7, on each clock cycle, it will try all those 8 bits before moving to the next cycle. So the way it progresses is cycle by cycle. Right? So in the semiconductor designs, we have this concept of clock and reset, right? We have this reset and clock. Clock is a pulse, right? We all know that, right? keeps going like that, right? Reset is something, a mechanism to basically put the design in a known state, a known starting state, well-defined known starting state. Right? Otherwise, when the design powers up, we don't know which state it is going to. So the way formal progresses is clock cycle by clock cycle after the reset. So when the reset is gone, power up, then we put reset on, then remove that reset, right? Make reset high, and then make reset high, and then put it low, right? After this point, the design is ready to operate, right? The way formal works is that at each clock cycle, it tries to drive all the possible values. But because of that, it becomes easier for formal to cover the formal cases because it's
But that take too much time.
yeah.
So how to do?
Yeah, some of the input combinations might be out of the defined legal space, right? For example, let's say we have two inputs, right? There might be some combination that only one, if one input is 4, then other one can be 10. It cannot be 4. So we may have to filter those out. So we have to, in formal we have to do that. So in simulation, we had to add, we need to add stimulus. In formal, we need to subtract. Right? So in simulation, we start from 0. And then keep on adding. In formal, we start from infinity and then we keep on reducing. So let's take an example how the state space is covered in simulation versus formal. So let's say we have this reset state R in the design. In simulation, let's say from the reset state, it can go to 3 possible states in the next clock cycle after the reset, of course. Not talking about the time in the reset. In simulation, it will pick it, depending on the inputs that are generated, it will go to one of the states. Right? Let's say S10. In formal, it tries all the possible values, so it will cover all of them in a single run. In simulation, if you want to cover this, you'll have to do some different runs, and then the simulation tools have this concept of seed. You provide a seed, it will go to one path. You provide a different seed, it may or may not go to a different path. You don't know. You'll have to figure that. I mean, there are means to monitor that if it went. I mean, which path it took. But
So it's generated random. So some randomness there.
yeah, in simulation also there is some randomness. There is also some randomness. I mean, it generates some random inputs, but you cannot always guarantee that. In formal, it's automatic. I mean, before moving to the next cycle, it will try all the possibilities, and it keeps on going like that. So in simulation, in a single run, it will just cover one of the path. In formal, it will keep covering all the possible paths at each class. So it will keep going like that. This is the reason formal. With formal, we can cover those corner cases first. Because of that, we needed those re-spins or.
So what happens in the formal picture if there are too many leaves? I mean, I don't understand how you can cover this in a linear time. It's like how are you traversing the tree?
Yeah. So like Piyush earlier said that it might be too complex, right? It might be too complex to cover all those cases, right? Actually, that happens. So sometimes it is possible that because of the complexity, it is not able to reach up to some states. Let's say it stops at sometimes right there. After that, no matter how much time you give, it cannot move. So that sometimes happens. So because of this nature, but it is able to catch those corner cases much easily. But still, I mean, formal usage is pretty low, and this methodology has been in the industry since mid-90s. Still it's very low, and the reason is those challenges that that comes with formal. So whenever you remember, we have that generator, and then the right side we have these checkers. In formal, whenever we run the tool, we run those checkers, and the checkers they progress cycle wise. What do they tell? That okay, starting from reset, went to cycle 1, cycle 2, cycle 3, right? If they are able to find something, some case where the design is not matching the expectation, then they give us a failure. They give us a failure, which comes with a cycle number, let's say 10, the cycle number and it's 10, which and that gives us the complete trace basically for us from the reset step to that 10th cycle for us to see.
How is the failure detected, sir? When does it say that it?
So we have these checkers, right? The checkers are something that we need to provide to the tool. And the checker says that the checkers we write based on the specifications that we had earlier. We had those specifications, then we had that design in hardware description, right? Based on the specification, we come up these checkers, right? So a very simple checker. Let's say some signal is high. Very simple example, some valid signal is high, right? And then the specification says that let's say 2 blocks A and B. Let's say A is producer of some signal, B is consumer. A sends this valid to B, B is the consumer, it sends ready to A, right? And the protocol, there is a protocol between A and B that A, once it sends a valid, it keeps on sending until B says ready, right? Ready means that I have taken care of it. So a very simple checker for this will be that once valid is high and ready is low, valid is high and ready is low, valid is high and ready is low, like this. Then in the next clock cycle, valid will be high, right? If we are writing a checker for this, right? Make sense? This is a very simple combination. Right? We provide this thing to the tool and along with the design that okay, show me if this thing follows this behavior or not.
And you provide like this kind of formula, like
Yes. We provide this formula. And say that okay, show me if this is follows up. This design is following this thing, this behavior or not. If it is able to find some case where this is violated, that means that will be a failure for us. If it is able to determine that okay, no matter what, for all the
but this when you write this, you will write it over all time instead of something like for all time
yes,
times. So it's like the formula is with the quantifier.
yes. At each clock.
But sometimes when you write it, so with the tool will have one formula, like the first order kind of with the quantifier, or like one formula per time step or something. So there are two ways of writing this. Like, so one could be that I write it like so at time 1 this has to be ordered, and time 2 and I write this separately.
Okay.
So just like
So the way we do it we provided the tool is at the clock edge. So we have this clock signal, right? This clock signal, right? Let's say
also you have an and clock edge.
yes, at each clock edge, check this. At each clock edge, check this. It is being followed. And if that tool is able to determine that okay, for all the space that all the input space that we have allowed, under that space, if it's able to find that okay, this property is going to hold, then of course it can give us that 100 plus. And there might be some cases where this unbound, we get this bounded pass. Bounded pass means it is able to determine that, okay, for let's say n equal to 20, up to 20 cycles starting from that reset state, that this property holds. But after that, tool is not able to say anything.
So this is what in the 30 was,
Yeah.
this is to stop, but that.
So, and when this happens sometimes, I mean, the first thing to do is to increase the runtime, of course, but there comes a point after which, if you increase runtime, I think the things. This is the reason actually. This is the reason they use. This is the reason. The usage is still low because many people, I mean, mostly people do not understand what to do after. That's
And who writes these tools? These are in-house or you get it from
We-
some other companies produced?
Yeah, so we have EDA companies in semiconductor industry. So like Cadence, belongs to this, so they provide those commercial tools. I think there are some university tools also available for people to use, but I think they do not. I haven't tried those. But as far as I know, they require some their specific language, to use. You cannot use them with the commonly used languages like Verilogix and whatever that are commonly used in the industry. I think we already talked about this. There are some complexity solving methods that we use. So whenever we come up with bounded pass, we need to do the analysis. We need to do this analysis that if how can we help it do? How can we help it do? There are various methods to do this. I'm going to talk about some of them, and then these three methods. But these three methods help the tool a little bit, but they doesn't guarantee that we are going to get to the state of unbounded. So many times we have to take this engineering decision. I am calling this engineering decision because the tool is not able to give us this unbounded path. So there are other means to analyze basically that if we have covered sufficient spaces or not. Things such as which are called code coverage, functional coverage. Like if we want to some scenario, like if we want to see that okay, this design has this state machine. This state machine is able to move to some other state that we are able to see that the state transitions. Okay. We collect these kind of coverage data. This kind of data is called coverage data, and if we have some sufficient coverage data, and we feel confident about it, then we take that engineering decision. And this happens with simulation also. At some point, we have to take that decision. Now, yeah. So coming to the complexity solving methods, one of the most easy method I would say is DUT, shrinking the design under test. If it is parameterized, can you shrink that? Shrink those parameters. Remember the complexity for the tool. I mean this bounded pass. Whenever this happens, we call that tool has hit complexity. That checker has hit that complexity. The complexity happens because of the two reasons. Mostly, actually, yeah, we can say two reasons. One is the Bradford search that we saw earlier, and then this Bradford search, along with the number of state elements in the design, the complexity gets increased exponentially.
So, like, typically, how much code coverage would you be satisfied?
Depends on many things like the nature of the design, right? What kind of design we are using, right? How old is the design? Okay, if the design is a legacy design, a 10-year-old design, then people actually get relaxed a little bit. But if I talk about numbers, somewhere about 90 to 95%, if people are able to reach that.
This is code coverage of the HDL code, a very long code in what the tool ran.
But it depends, I mean, situation to situation, I mean, sometimes. Could be some business fixing as well. Yeah, so DUT shrinking. So one of the easiest method is DUT shrinking. So what do I mean by this? Let's say we have this design, okay? Inside the design, let's say we have some pipe question, some pipe. We want to verify something which is of course at the output, and this FIFO is, let's say, in the fan input, right? This by fan in means this logic has some influence. We want to ensure that the other logic, okay, the other surrounding logic of this FIFO is able to handle those conditions as well when the FIFO is full. If the FIFO is very deep, 128, let's say. And we are not able to see that because to fill this 128 FIFO maybe it will need many cycles, and we are not able to. One pretty easy way, if is to shrink this FIFO if given that the FIFO depth doesn't affect this function. It might affect this when it comes to performance. Maybe FIFO is there. I mean, the FIFO depth is a decision of performance requirement. In that case, we can do it. There are some other cases also that we cannot do that, but yeah. So if that's the case, and if we are able to do this, we can try that, right? What this will tell us that, okay, if we let's say reduce it to some smaller number, let's say 60, and if we are able to see that full, and we are able to see that, okay, the surrounding logic is able to handle that situation as well, then we are good, right? We are good on this part, right? We have seen that convention. The other method, commonly used method, is assume clarity. Let's say we want to prove something. We are writing the checker something, right? From the inputs to the output. And this whole checker is getting into complicated issues. We use this method called assume clarity, where we break the checker into multiple blocks. So this is a very simple method. So break the checker in two parts, from here to here, and then here to here. Prove this, assume this, prove this. Easier said than done because because doing this requires a deep knowledge of the design microarchitecture, and it also requires that it also actually comes with the requirement that we should be able to define some checker at this. Some internal is sometimes so it's very hard.
But this is like at the level of cycle. It's not the level of cycles, it's the level it's a cut in the circuit.
Cut in the circuit. Some point in the circuit where we can define something. Right?
So instead of checking the final output, you are checking something in it.
Yes. So as a first step, instead of checking final output, I am checking something in between. If I have to find that, and then I will assume this, and then I will prove this.
But finding this itself can be pretty hard. Like what is the best?
Yes. This is very hard. That's why I made this easier. The third is abstractions. Third method is abstraction. So this also is quite hard in terms of implementation, because it also requires
like is that like services kind of thing? This result in complexity theory which does something similar.
Yeah.
Breaking in that.
I mean, it's a divide and conquer.
Yeah. Because there is no about it.
Composition.
Sorry.
yeah. So the third is abstractions. Third method is abstractions, where we put some additional behavior into the design and prove the checkers with that. So what we do is that there is some design component. We put instead of that, we put an abstraction there and then run those checkers. And abstractions with the nature that they are the super. And any checker which holds with the abstraction would hold with the true would hold true with the design also because of abstraction needs. So for example, yeah, I'll give some examples. Before that, before going into the examples, since we are adding this additional behavior, right? The checkers might give us false failures, right? It gives us a failure, but that failure may be because of that additional behavior that we added in the abstraction. So it needs fine tuning. If we make it too abstract, at some point, let's say we make the design behavior too abstract, like the very abstract thing will be to keep this output undriven, right? Nobody drives it, which is an abstraction, which is an abstraction, right? Because it can take any value, right? It can be 0, it can be an abstraction, but of course, it's going to give us a lot of value. So we want to keep the abstraction not too coarse because that will give us false failures, and at the same time we do not want it to too fine, otherwise it will replicate the RTL behavior, which will again come up with a complexity. We need this fine balance. Basically, we need this careful tuning. And this, because of that, it takes a whole lot of time. Depending on situation to situation, it takes sometimes a whole lot of time to add an abstraction. So let's take some examples. Let's say we have this state in the design. We have this state R is reset state, and then from the reset state, let's go to these many states. Let's say we run
Each arrow here is one clock cycle, and is that
each arrow, yeah, you can say that. Actually, not necessarily, but for our discussion. Let's say we ran some checker and we are not able to see, and then we got a bounded pass, and let's say we are not able to see this condition. Now, one way to solve this is adding this additional behavior that instead that the DUT starts from R, we add this additional behavior that instead of R, we allow it to start either from R or S. So it's the tool, we give this choice to the tool. Okay, make a decision, either start from R or from S. Since the tool tries all the things, it does both the things. If it chooses this condition, we are able to see in the single also. But again, this is also very not that easy to do, because one state machine, let's say we are starting from here, it may require other something in the files, right? Write something. When the state machine goes to this Sn plus 1, let's say this state machine also reads based on that state, right? Now, if we start from that state Sn, FIFO might be empty, right? And next it goes to SN+1 and reads from an identifier who gets a garbage. So we need to take care of this case as well, right? If the state machine is starting from SN, this FIFO should not be anything, right? So now we need to include this FIFO also into the initial value, right? That out of the reset, FIFO doesn't start from an empty state. It starts from a state, and it has something. Another example could be a counter reset. Typically, how the counters work is generally in the designs they increment one or by fixed value each clock cycle. And let's say we add this abstraction, and we add this abstraction where we allow the counter to increment or make a jump, let's say, to the values more than one, okay? or more or less than that fixed value. This also helps us. So for example, if some important event in the design happens, let's say when the counter reaches when the value of 0 to 3, and let's say this starts from 0, minimum it is going to take this 100 to 1, but maybe more than that because it has some potential. But if we add that counter abstraction, we may be able to reach that in a single block cycle as well. Given that counter is not used anywhere else. I mean, if it is used anywhere else also, then we'll have to make those stops. Like the counter value of let's say 127 is also important. And then we have to make that stop. But then go from 0 to 127, stop there, and then from 127. Okay. This is another example. Makes sense, right? This is another example. Okay, or before going there, since we are already talking about the counters, let me give one more example. So again, this involves more practical use of this counter abstraction. So let's say we are verifying this AES, let's say some AES code, right? Sorry, AES design, right? By the nature of AES algorithm,
The intrusion.
intrusion. So it involves 10, 12 or 14 steps, right? Depending on it comes in the key size, right? If the key size is I believe 128 bit, it involves 10 steps. Maybe I might be wrong. 192 bits, then 12, and 256 bits, that's 14. So typically the way it works is that let's say we want to verify the control path. So we have this AES design that we have this control path, which is basically taking up all the control logic, and then we have let's say this AES engine, which is doing all this transformation. We want to verify that. This AES engine, if we give some input to it, it will give us the output in 10, 12, or 14 clock cycles, right? Depending on the key size. So typical way to implement this control logic is that once we give this input, we wait for 10 clock cycles, let's say. We wait for 10 clock cycles, and whatever comes up that after 10 clock cycles, we say that okay, this is the input. Now let's say we want to verify the control logic. For the time being, we are not interested in this. Let's say this is something given to us. And in that case, we can actually add this counter abstraction, right? Because we are just giving this input to it, right? Waiting for 10 cycles or for 12 cycles or 14 cycles, and then we are, then the design explores. So that this design waits for these many cycles. We can add the counter abstraction here, right? Okay, because the value from the point we give this input, the value of 10 to 12 or 14, depending on configuration, is important. Other values in between actually are not.
So nothing needs to be verified there.
And then everything needs to be. Another thing people actually get stuck at what needs to be verified, right? No, sorry, what needs to be extracted when we are writing abstraction because the designs are very complex. So I have this one pretty small example here, and this again involves a pipe. So let's say we have this logic, and we are running this one checker, and this is going into complexity. So we let's say analyze the coverage, and we say that okay, we are not able to see this full scenario, and now we need to see that the duty shrinking approach that is not going to let's say work here. We don't want that. So how do we do that? How do we now solve this? Is that we add some abstractions on this value. So let's say this 5.4 is 128 B, and we are not able to see this full, and we let's say this 5.4 is itself not parameter. Right? Maybe someone hard coded it or maybe it could be anything. We want to see this full signal going high, and that basically gives us some indications that we have to add this abstraction. So we can add an abstraction for the what we can do here is that instead, so the 5.4 full, this 5.4 full signal becomes high and the 5.4 occupancy becomes 128. Maybe we can make this 5.4 signal high on a constant value, right? On a constant value, which is also less than
That's even in the beginning, maybe it's already.
yeah, maybe some yeah, or in the beginning maybe we may get some false values, but yeah, that's also but let's say the 5.4 occupancy becomes 3 or 4, it's allowed to send this. So, but I mean, these abstractions again they need quite deep understanding of the micro architecture, which is itself a big task. So, this is the basically reason.
And this, so when you say this can understand, this is understanding at the level of VHDL, the variant of the code, like so what the modules in it.
Yeah. So yeah, both. So starting from the micro architecture, meaning that what on a high level, a little bit higher, not at the architecture level, what all those components are going to be, right? This is we are going to have these file or a scheduler, right? Now inside those schedulers, what we are going to have, we need to go to at a signal level, actually, to okay, with these kind of things.
So that is the netlist level, even.
No. Not less level, at the very low level, but at the signal level. The very low
Each wire.
each wire.
You would say the RTL level.
Yeah. Did I say RTL? Did I use the RTL word?
No,
Yes. Okay. I am, not using that. Yeah.
What is that?
Register.
Register transfer
Register transfer
level.
level.
So this is about the complexity and solving the complexity and why formal usage is still low, but still, I mean, there's a whole lot of potential that people there in the informal and its usage is increasing day by day. And the reason basically is that because solving complexity is quite a hard thing to do, but not impossible. Now, this picture we saw earlier in one of the previous slides, and in one question on this picture is that we use this formal simulation emulation at this level. Simulation is still largely used because of the complexity. People don't know how to solve that, but I mean, formal is increasing day by day. But here we see formal. No simulation.
And emulation was what exactly?
Emulation, you can say that we have this RTL, right? We port this RTL to the FPGA, big programmable data, and then run it. But it's quite expensive, and not everything can be verified here because of being expensive. There are some other reasons. So we have this complexity problem with formal here, but we do not have it actually. That's why formal is largely used. And why? I mean, at this level, we have this complexity, at this level, we don't. And the reason is, the reason is that, let's say we have this RTL now, I'm using it first time. The hardware description language. I mean, this is the if we look at the logic, we have these flip-flops or combinational logic, right? Like this. The way this synthesis happens when getting this very long gets converted into the netlist, the tools, I mean, of course, some of the flip-flops may get optimized, some of them fail. But still, mostly we can find a mapping between the RTL flops and the netlist flops, right? Once the tools are, I mean, even the tools are able to find these mappings, they map them. They do this mapping and then apply this as directly by itself. So user don't need to do anything.
So this is like in the software settings, you be like checking whether the compiler produced the correct machine code.
I am not that was familiar with, but yeah.
Is it?
So this is done automatically by
Yes,
some tools from
mostly,
RTA to netlist. And so this is also, I mean, so there is some like, so there are some compilers which also some people would write, and then some other companies will produce those compilers which.
By compiler you mean this
Yeah,
number
but
this
yeah. And which companies will make same the EDA.
So they transform this to this, and then we need to ensure that the
So one thing, so like in the software thing, we never do this step, right? So there is some compiler, and you run the compiler, and this and then you sort of trust that. So here, somehow that trust is not there. So is there a reason why this is?
probably because of money involved.
But
The program crashes.
can you verify the compiler itself? Like, I mean, that the compiler produces the correct translation.
Not the right person to answer that. Probably not. That's why they have it. Or probably because of the trust issues coming from the money. Because one reason causes millions.
Probably just adding redundancy so that.
Yeah. So this, because of this automatic, as you guaranteed, being implemented by the tool itself, never getting to. I mean, it's always. Now, yes, this was about formal. There are some limitations. So typically the tools that are available industry level, they are mostly not are good with control part designs, and not that they do not perform that well with the arithmetic, like the course itself. So earlier I took this example, right, of the AS engine. I said that okay, let's do not worry about this AS code itself. Right? The reason is that typically the tools available, they are not that much. They do not perform good with these kind of designs. But still, we can verify the control part of these. And
Control is like when is what
Yeah.
what registers.
And if the actual engine you would use simulation.
yeah, the actual engine, and then mostly in these kind of designs, it is very easy to verify using simulation because there are not many corner cases. The corner cases actually comes because of these parallelism, right? Because of the parallelism, additional things being done in the architecture. These kind of, we take this example of the encryption, let's say there are predefined fixed those steps, right? And putting steps, and this should be done. That's so usually it's pretty easy to verify the simulation. If we are talking just about the course, it usually verifies that. people don't have anything very similar. Though in the industry, they are coming up with some specific tools that can be used with these kind of designs, but not all. Not all. Some of the format tools actually can verify multipliers, dividers, some specific architectures of multipliers.
So why it's a big challenge there for these things?
The data point.
Yeah.
Probably that has something to do with the formal and the algorithms that go and that work and that do.
For SAT formulas are much more complicated.
Probably. You remember that is now? This is one. I mean, at a bigger level, at the system on chip level, it's again the design size is too large. For a tool. So currently available tools, they are hard to the system. But still, we can verify some things like connected features. That everything is properly connected. There are some other formal apps. I mean, the tools provide some specific apps also. For example, apps propagation check, which basically means that in the circuit, at any point, it is not propagating in any unknown value to the output. So they have these kind of apps, then clock CDC, clock domain processing. So nothing wrong happens in the signal process from one clock domain to other clock domain. The design can have multiple clocks. Some of the designs have multiple. Where the signal process from one clock domain to other clock domain, it doesn't get corrupted. And then of course connectivity check. And then this is something people have done at universities level. Basically they do this quick early detections using formal tools. Typically CPU designs.
So what would that do? So what is I forgot the example, but they do something like this. They have this one operation, let's say load some register R, some R2, addition of let's say register R1 plus register R3. So what do they would do in this, that they'll replicate this. They'll replicate this operation. They'll replicate this operation into some other register as well, and then they'll try to combine this. I have never done that. I know it. I think that's it. And
So like how good are the state of the art tools, like say for simple designs, do you need to kind of, you just go through completely and then kind of.
Depends nature of it. Depends nature. Right? I have heard, I will never tried, but I have heard someone tried to write a very long code for solving this Rubik's cube. It has, I believe, some 26 steps, so 26 states involved. Even that the tool at that time, it was way back in 2013 or 14. But that time tool were not able to completely solve that. I mean, completely give us. But only 26 design. But sometimes, what I've seen is that typically speaking, the tools are able to handle the designs. I would say about 20K flip-flops without much abstractions needed to it, and without needing much abstraction. But beyond that, of course, we will have to. But this number I'm just saying doesn't, I mean, not guaranteed anything because it's just they'll remember. Typically the best design to do.
More questions? I think I'm trying to start with.
Hopefully it was.